In this video, we'll explore the FluidFX settings that can be found in the X-Particles Emitter. We'll explore surface tension techniques. We'll set up some viscous fluids. And we'll do some granular simulations. So let's get started. In this scene, we have this piece of collision geometry. And this is obviously being animated, and we've got it animated by a vibrate tag. Let's just have a look in our colliders folder. And we have created this nice vessel using the lathe tool in Cinema 4D. It has an X-Particles collider tag on it, and it has a vibrate tag attached, which is giving us this nice little bit of movement. So what we are going to do is we're going to emit particles, so we fill up this vessel with fluid. So let's just look at our emitters. We have two different folders here, and for the time being, let's just ignore this bottom folder, and we're going to look at this one that's called equal density, and we'll explain what that means in a moment. So first of all, if we just activate emitter 1, here is our emitter. And if we go to our XP FluidFX, which is in our Dynamics folder, you can see that this, if we have a look at the attributes, this is set to completely default settings on the fast accuracy preset, but the only thing that isn't default is that we have check density active, and that means we're going to get a nice consistent stream of particles from our emitters without any of that kind of pressurized force. So let's hit play. And we can see, because we've got a gravity in the scene, the particles are being emitted and they are sloshing around in our animated vessel here. And they're behaving like a fluid volume because obviously our XP FluidFX is doing its thing. So let's just activate emitter 2, which we can see here, positioned slightly differently. Now this is going to emit a little bit later. So first we get our orange particles. Then we get our blue particles. So we have two different emitters here, but these are both being solved, all of these particles, by the XP FluidFX solver. And you can see that the solver doesn't care whether the particles are orange or blue. It doesn't care which emitter they have come from at this point. All of the particles have been considered to have the same fluid properties, and so they're all kind of mixing around the place and sloshing around as one fluid entity. And that's because all of the fluid settings are the same in all of these emitters. Let's just activate the final one, emitter 3. We've got some green particles. And so, you know the drill now. We've got our orange ones, then our blue ones, then our green ones, and here they are sloshing around. Obviously our container is filled higher now because there's more particles there. And now let's just pause it. I'm not sure if you saw that. Let's just run this through again. Now, at around frame 300, we got a couple of what look like leaking particles. Let's just have a look. Keep your eye around here. It's a couple of orange, but yeah, look, you see these two orange particles? They've managed to escape this container and they've fallen down. So obviously that isn't what we want. So the reason this has happened is because our collision object is animating via our vibrate tag. And it's animating, it's actually the rotation of this which is animating. So even though it doesn't look like it's moving that vigorously, actually because it's rotating, some of the individual points on this bit of geometry are actually moving quite a long way frame to frame. And that means that we require more sub-steps in our fluid solve. We need to kind of split that animation up into smaller steps to make sure that our particle velocity solve is accurate enough, because at the moment it isn't, and we're losing these two particles. So the way in which we would solve this, there's a couple of things that we could do. First of all, we could just make it a more accurate solve, putting more sub-steps into the simulation, and that will solve the problem. So let's just demonstrate that first. It will go to our XP FluidFX object. Let's go to the accuracy settings. Let's just put it on medium from fast. So this is going to give us more sub-steps. Hit play. And a couple of things are going to happen here. This should be enough substeps to stop that leaking. But what you're going to see is, because we've got a more accurate sim, look, there's less compression in the fluid. And this green particles have actually come out at the top of the container. Because look, the water level is higher because there is less compression, because this is a more accurate simulation. So for us, this way of solving that issue of the particles escaping isn't going to work. So what else might we be able to do? Let's put our accuracy back down to fast. So what we can do is actually kill these particles, because there's only a couple that are escaping. Killing them isn't going to hugely change the way in which our water body is simulating. So you can see in this scene that we have an XP kill modifier already set up. If we go into that kill modifier, you can see that the kill modifier, if we make it visible, here are our kill bounds, the green bounds, and we are saying that if any particles stray outside of these bounds, they will be killed. So that obviously isn't going to work for us, because we want to get rid of these particles as they leave our container. Well, we could change this from outside bounds to objects. Then we could drag in our lathe object, which is our collider object. And we can say that particles which are outside of the object should be killed. The problem with this is, because the particles they're being emitted from outside of the object, they're just going to be killed immediately and we have no particles. So to do it in this mode, we would have to animate when the kill modifier is enabled. So let's just demonstrate that quickly. So now it's not enabled. We can press play, fill up those particles, and then at this point, we can enable it. Particles are still there, but as soon as they leave our lathe object's volume, they will be killed. And that means that we're not going to see those escaping particles. And look, that's because they've been killed. So that has worked. But it's not the most elegant solution, because we're having to keyframe this enabled on and off to allow our container to fill up in the first place. And one problem with that may be that at the beginning of our simulation, what if we got a bad velocity solve here whilst they're still filling up and we wanted to kill off a particle? If we enabled it, it would then stop these particles from being emitted effectively in the first place. So that isn't going to work. So let's just remove that lathe object from the objects window. So what we're able to do is use, if we just come down in our kill object, we have an isolated option. And what this will do, it will only kill particles if they are isolated, if the particles are on their own. So if we click on isolated, it opens up this distance. So this says if they are this distance away from another particle or greater, it will be killed. Now at this point, if we have it on the default 10 centimeters, what's going to happen is if I hit play, we're going to see, oh, actually we haven't got our kill modifier enabled. So let's enable it. Let's hit play. And you can see, look, they're being killed immediately. Why are they being killed immediately? Well, that's because our particles have a radius of 8 centimeters. So their diameter is 16 centimeters. So even if particles are touching, the kill modifier is thinking that they are isolated because they're within this 10 centimeter distance. So if we raise this up to, say, I don't know, 26 centimeters, it's going to allow the particles to be emitted. But then if any particle becomes further away than 26 centimeters from another particle, it's considered isolated and it is killed. And there we see that we've solved the problem of our particle escaping the container because we've killed them off because they are considered to be isolated particles. So that's one way of doing it, and that's going to work in this instance. Let's just switch off that for now, and we will put that back to outside bounds. Let's make that kill invisible. And there we go. Now we're back to where we started. So if you are getting particles that seem to be leaking from collision geometry, then you either need to increase the accuracy of your solve, which creates more substeps, which means that velocity solve can be solved correctly and you won't get the leaking, or you can set up a kill modifier in various different ways to kill off those stray particles and make sure that we don't have them leaking in our scene. So this is the key as to one of the reasons why XP FluidFX is so versatile, because we can have one solver set to whatever simulation settings you require in the attributes, but then we can give particles from different emitters different fluid properties. So let's explore that. What we're going to do is turn off all of these equal density emitters, and we're going to go into our folder which has 3 emitters with a varied density. So let's look at what that actually means. Let's make a little bit more room in our attributes. So if we go into emitter 1, these are in exactly the same position as the other emitters, and they are set to emit the same amount of particles at the same time as the other emitters. But if we go to our XP emitter, we can go to the Extended Data tab here, and you can see that we have a Fluid Data tab. Let's click on that. And this is where we change our XP FluidFX fluid properties. And we have various different properties. We have the fluid type set to liquid, which we'll leave on liquid for now. And then we have the ability to change these settings. We've got a density setting, a viscosity setting, 2 vorticity settings, and a surface tension setting. And these are all on default, apart from this density setting. So in our orange emitter, we have given these particles a density of 6,000, which is high. By default, this is on at 1,000. So then if we move on to emitter 2 and go into the fluid data, you can see that all of the settings are the same, but the blue particles have a density of 2,000. And if we go into emitter 3, the green particles, they have a density of 1,000. So the orange ones are more dense than the blue ones, which are more dense than the green ones. And look what happens as a result of having particles of different densities. We get our simulation, and look, the more dense particles sink to the bottom of our vessel. The mid-density particles are above that in a layer of blue particles. And our particles with the lowest density value, the green, are floating on top. So now with one fluid solver, we're able to get liquids realistically mixing of different density values. And so we can simulate things, if you imagine a lava lamp with oils floating around in a water body. And very quickly, we're able to get what would be quite a complex simulation here to get these mixing densities. We can get this set up very quickly and very easily just by adjusting one of the parameters in the particle emitters fluid data section. So this is incredibly versatile and very fast to set up. And of course, the density value here is having an effect on XP FluidFX's density calculation, that fluid density calculation that XP FluidFX is making. So again, the same rules apply. To get more accuracy in this density solve, we need to increase the accuracy of the simulation. So for example, if you're on fast and you're mixing density particles and you're seeing some particles perhaps getting trapped. Look, we've got one green particle here which hasn't been able to find its way up to be with its fellow low density green particles. That is suggesting that that fluid density solve hasn't had enough iterations to solve accurately. So what we could do, look, let's move this on to say high accuracy. Let's run through this simulation again, and this is going to have a more realistic fluid density solve, which means that we're going to have a slower simulating scene, but those fluids are going to mix and settle in a much more realistic manner. So that is one of the areas in which we're able to manipulate separate emitter settings for specific results. And that is the first parameter that we've explored, is this density value. So now let's have a look at one of the other values here, and we're going to have a look at a very important parameter. This one is going to be surface tension. So to do this, what we'll do is jump into another scene, and what we're able to do with surface tension is a very useful parameter, because we're able to, even at quite large scale scene values, we're able to mimic a very small scale fluid simulation with this. So let's have a look at what we have here. If we hit play, you can see that we have an emitter, and we've got some fluid particles falling down and interacting with an invisible plane that's in our scene. And you can see we're getting a kind of a splat of those water particles. Let's just have a little look at this scene. So what we have are, we've got a series of different emitters, but at the moment we're just using this one that's called emitter drops, which is our box emitter. We obviously have a gravity in our scene, and we have an invisible floor plane here, which is what those particles are colliding with. If we go to our XP FluidFX settings, we are in the default settings, although we do have check density active, but because we're only emitting on one frame, actually this is irrelevant. So if we hit play, the particles interact, and FluidFX in its fast accuracy mode is making these particles behave as a fluid. So let's have a look at our emitter settings. If we go to our XP emitter, this is where we access the fluid properties, and we go to the extended data tab. Let's go to the fluid data section, and you can see that here we are on default with density of 1000 and so on. And we're going to look at surface tension. So by default, surface tension is set to 3. And what surface tension does, the stronger the surface tension, the more likely the particles will attempt to inhabit an area which gives the overall volume of particles the smallest surface area possible. And with very high surface tension, we begin to get a beading effect. So let's have a look. That's our surface tension on the default, which is 3. But if I put our surface tension up to this midpoint at just under 250, watch what happens. They splat down, and then look, they start coming together as those particles are trying to inhabit a space which means the overall volume has the least surface area that is possible. So if we increase this surface tension to the max and hit play, they're going to contract even more. But they get to a point where they can't inhabit less space. Now, if these particles, they're only kind of in one particle thick, this layer, if they were actually piled on top of each other, they would be a part of a volume which would have a much smaller surface area. But they're not able to get to move into that point because they're fighting against, the solver's trying to get them to do that, but they're fighting against this gravitational force which is forcing them down. So the solver just doesn't have enough strength. But if we are to increase the solver's iterations per step, it's going to give it the ability to do that. So again, this is a situation where our scene requires more simulation accuracy, more solving iterations to get this to work. So look, if we change this to high, this means that we have more sub-steps per frame, which means we have much more iterations per frame. And now if we hit play, you're going to see, look, our surface tension is able to blob this up into what looks like much more of a beading droplet. And if we put it onto accurate, which means we've got even more iterations, it's able to move around until it has created this droplet with very high surface tension, meaning it's taking up far less surface area, this shape, than it was when we had our two-dimensional splat. And we can really see this happening. So if we, for speed's sake, let's just put this in high so we get slightly quicker playback. Let's go to our emitter drops and drop that surface tension back down. Let's return it to the default 3. And we hit play. And there we have just our splat of water. But if we have our splat of water and then increase that surface tension, we begin getting them moving towards, and if we increase it, gradually they're moving to inhabit this space, this volume, which has a much smaller surface area. And so what we're able to do, even at a relatively large scale in our scene, look, if we put a default Cinema 4D cube here, this is a huge cube. It's 2 meters across. So it's a massive cube. So if we delete that out, so this is a very large blob of water. But by increasing that surface tension, we're giving the simulation feel of a tiny droplet, which has created this bead of water. So if you're having to put a realistic, very small scale fluid simulation into a pre-built Cinema 4D scene, which is actually quite large in scale, we have the power of being able to do that by manipulating these fluid properties in FluidFX. So this is really powerful and it's looking excellent. So let's try with a different emitter type. So we'll just deactivate our emitter drops and let's go down into our texture emission. So what's happening here is this emitter has been set up to emit from the texture in this plane. So it'll emit from the white areas and it won't emit from the black areas. So let's just make that invisible. We'll activate our emitter. And if we hit play, now we're getting these particles falling down. And there's not really an awful lot of beading going on there. They're just kind of the water particles are being solved by FluidFX. But why isn't there much of that beading? Well, this is because we can tell that, look, it doesn't have a very high surface tension value. So let's go to our emitter beading options. We'll go to the extended data. Let's go to the fluid data so we can look at the FluidFX properties. And yes, look, we only have a surface tension of the default 3. If we increase this, look, we start getting beading. If we increase it even more to the maximum, we start getting that 3-dimensional beading because it has enough iterations to be able to fight against that gravitational force. And now we've got these real kind of water droplets beginning to drop down from our texture. So again, we're mimicking this very small scale water beading effect in a scene which is actually large in scale. And we can, of course, animate these. So in the real world, obviously you can't, but we can get some incredible effects merely by animating this surface tension value. We can get that water beading and then falling back into a liquid and then beading with greater surface tension again. And so it creates a very versatile look, and we can get this really nice beading effect. For example, you could use this if you wanted to simulate some condensation beading and dripping down a can for that kind of product shot that we all know. So that is a very nice example of beading. Let's just show a different example. And this is obviously the same technique, but now we've got just different emitter types. So here we have an emitter which is a torus. And if we hit play, you can see there we're getting some nice fluid being emitted from this torus shape. And if we go to our emitter torus, we'll go to the extended data, fluid data tab, and increase that surface tension. And we're going to start getting these big beads, which minimizes the scale feel of the scene, which makes it look like this is a much miniature, smaller scale scene than it actually is. And if we just make that one invisible, and we also have an emitter, which is emitting from this star shape, and we get a similar effect. And if we go to our emitter star, extended data, fluid data, we're on the default surface tension of 3. If we want these particles to begin looking like they're fluid beading, we can put that surface tension way up, and now they bead as they come off this star. So surface tension, a very powerful effect, which if you manipulate it and understand how it works, it can be used to simulate very, very small scale water sims, even in a sim that isn't particularly small scale. So now let's have a look at another effect which is incredibly powerful within XP FluidFX, and that is adjusting the viscosity setting. And this is great for making thick, gloopy liquids. So what we'll do to explore that, let's go into a new scene, and we have a viscosity scene set up. So in this scene, it is pretty simple. We've got 2 colliders. We've got a floor plane and this kind of angled cuboid. We have an emitter that has a vibrate tag on it, and that emitter is actually in an animated null as well to give it a bit of interesting rotational movement. We have an XP gravity in the scene for those particles to fall downwards, and we have an XP FluidFX solver. So if we just have a look in the XP FluidFX, you can see that we're on default settings here, apart from we have check density active because we want a nice consistent stream of particles. And let's hit play. And you can see that we've got this pink liquid, which is kind of splashing down. We've got a very high friction setting on our collider tag. So some of it's sticking to this collider, but this is behaving like a watery, runny liquid. It's not thick and viscous at all. So let's have a look at our settings. We'll go to our XP emitter. We'll go to our extended data, fluid data tab, which is where we adjust our FluidFX fluid properties. And we can see that the viscosity is set to the default 30. So let's just remind ourselves what that looks like on default. So we've got a splashy liquid, we've got some sticking to the very high friction collider tag. Let's increase the viscosity and put it up to the maximum slider value of 1000. And you can see that we're starting to get a bit of a glooping effect here, but it's not a stiff, gloopy liquid by any means. And that's with a massive viscosity setting of 1000. And the reason is, similar to surface tension, is to get an accurate viscosity solve, it requires lots of simulation iterations. We need a very accurate FluidFX solve to be able to solve accurately a viscosity value so high. So let's go to our XP FluidFX and let's just change our accuracy fast, and let's put it on the top one, the top preset, accurate. So this is going to have loads more steps per frame, and as a result it's going to have loads more of those solver iterations going on. And let's see the difference. And now we can clearly see a very, very gloopy, sticky liquid simulating here. It's resting on top. It's gradually sliding down in this nice organic way. And look, as our emitter rotates in that animated null, we're starting to get these folds of gloopy liquid appearing and laying over the top of that collider object. And you can see that we're getting this really nice, clear, gloopy effect. And we can, of course, get this to be even stiffer. If we go to our emitter settings, we can go above this maximum slider value of 1000. Let's put it on 3000 and see. Now, this is going to be thicker. But it's going to get to the point where, to get it to be even thicker and keep more of a rigid shape, we're not going to be able to just keep increasing this viscosity amount. We're going to have to make the simulation even more accurate with higher settings than we're getting with the preset accurate amount. And the only way that we can do that is to actually go to the custom options. Now, in this training, we're not going to go into detail about setting custom options and exactly what all these different custom parameters mean, but we can just quickly jump into custom. And now we have opened up the ability to set the minimum and maximum steps, the minimum and maximum iterations, and then how the solver uses the amount of steps between this minimum and maximum is dependent on this CFL value, and how it uses how many iterations between the minimum and maximum is dependent on our compression limit. Now, this is a relatively complex theory, which we're not going to go into now, but just to kind of brute force a more accurate solve here, what we're going to do is say, at a minimum, the solver has to use 40 substeps per frame. That's the minimum substeps it can have, which means that because it's got so many more substeps per frame, it's automatically going to have lots more iterations per frame. So let's hit play. And you'll see that we've got a slower solve. That's because there's more calculations taking place because we've increased these minimum steps. But what you're going to see is, because we have a more accurate solve, we've got more iterations going on, we have managed to get a much thicker, more gloopy, viscous material. It's really holding these folding, defined, gloopy shapes more. And that's because we've given it the ability to do that, because we have massively increased the solver iterations, because we have brute forced it and said, look, at a minimum, you've got to do at least 40 steps per frame. And then you can see we can get this gloopy. So we can make this liquid more and more and more thick by increasing the viscosity amount in the emitter itself, the fluid properties, but also by throwing loads more solver iterations at the simulation, which makes it a stiffer sim as well. And the power, of course, of FluidFX is that the fluid properties are dictated by the emitter, which means that we could have multiple emitters in a scene with various different viscosity values, which means we can use this to mix different fluids, like you could get a molten chocolate that would be thinner and less gloopy than a whipped cream, for example. So that is how we can adjust the one of the other fluid properties in viscosity to get those really nice gloopy liquid effects. So now let's have a look at our vorticity settings. And to do that, what we'll do is go back to our drop tank scene. So if we hit play here, remember our drop tank scene, and we've got our nice, this is a large scale simulation, of course, and we've got our particles making their way down. We're getting this nice splashing, and we've got them filling up our containers. And we've got this in our XP FluidFX is in its fast accuracy, so we're getting a really fast solve. So let's have a look at what our vorticity can do. And what this will do is it'll accentuate kind of swirling motion in your simulation. It'll create really nice kind of little eddies of swirls, both on a small and a large scale. So to demonstrate that, let's go to our emitter water. And of course, we'll go to our extended data, fluid data tab. And let's just have a look at this sim. So at this point, we can see that we have a little bit of movement and swirling in this area of our simulation. But let's put our vorticity small up onto full. Let's re-sim. And what you're going to see is that you're going to start seeing some much finer swirling going on. And you will see that as the vorticity develops, we're going to get some lighter coloured particles as that vorticity moves. And here we go, starting to get a few swirls of vorticity. So to make this more obvious, let's go to our FluidFX and change it to a medium solve to give us a little bit more accuracy. And we'll play this through. And here we come. And as we're developing, so we're getting these nice natural swirls which are happening anyway, but then we're getting some more vorticing happening, which is a result of our vorticity small. So look at all of these various different small swirls of particles happening, and that is what our vorticity setting is doing. We're getting these individual small eddies, which are giving us some nice detail to this. So if we take that vorticity amount down to the default and run that same sim, you will see that at that point, we're no longer going to have those nice, tight, accentuating swirls. We're getting these big, large ones naturally from the splashback of the fluid hitting this wall. But as this develops and comes down, look, we're not getting those very circular swirls that we were. Let's increase that vorticity small and put it way up. And you can see now that we've got that input, we're starting to exaggerate this swirl here, look. So what the vorticity will do, it doesn't create this movement from nowhere. It needs an initial velocity input, but then if that initial velocity input is the correct motion, it will then exaggerate that motion over time, which means it develops into these nice swirling eddies. So that is what our vorticity small does, and it gives us these smaller scale eddies, and obviously the vorticity large creates larger scale swirling and eddies in our simulation. So that's what we can do when we're adjusting in the emitter settings, the extended data, fluid data, and the fluid property of vorticity. So now let's look at our final fluid property, which is accessed via the emitter. And to do that, let's go to another scene, and we're going to have a look at granular simulations. So in this scene, we have an XP FluidFX dynamics object here. Let's just click on that. And what we are going to do is we're going to work with our accuracy preset set to the highest level it can, which is accurate, because for good quality, accurate granular solves for things like sand or snow, then the solver really needs to have lots of simulation iterations. It needs to be a very accurate sim to get this to work in a way which gives us the best results. So we're going to straight off the bat, we're going to start with our accuracy in the accurate mode. It is possible to get simulations working with the faster simulating presets, but to demonstrate what the different granular settings do, it's easier to demonstrate those and the differences when we change the sliders if we have this in the full accurate preset. So we are going to leave the FluidFX settings at that for now, and we're going to go to our emitter. So in this scene, at the moment, we have an active box emitter, which is this purple emitter. And here is a collision surface that we have here. So let's just actually get rid of this hood element there for the surface tension. So here we have our emitter, and what it is set to is, if we go to the emission tab, it's going to shoot the particles out on one frame, on the second frame, and it's going to distribute them in an hexagonal grid, and the particles have a radius of 1 centimeter. Now, a couple of things. A hexagonal grid is the ideal way of emitting particles when you're doing a granular sim, because it's birthing those particles so they're tightly packed together without intersecting, and so there's very little wasted space, which means we've got a really good packed starting point to then have our object behave like a kind of a granular object would. So hexagonal is the ideal shot type when we're doing a granular sim, and also in FluidFX granular simulations, and in fact in all FluidFX simulations, it is best to work with particles all with exactly the same radius value. This way we're much more likely to get a stable sim. So that is what we have, and then we have our box emitter, obviously, and we can see this is just a simple bit of collision geometry. So we've kind of got a bit of a bumpy slope that we've created here, and there's also an invisible floor plane, and we have a gravity modifier, which is going to obviously be pulling these these particles to the floor. So let's have a look. We have our emitter box. We'll go to our extended data tab, and we'll go to our fluid data. So for the first time, in all the other simulations that we've been doing in this training, we've had the fluid type set to the default liquid. But now we've got it set to granular. And you can see that when we have it set to granular, the vorticity and the surface tension parameters are grayed out. They are now irrelevant. And we have 3 new parameters which have appeared. We've got friction, stability, and cohesion. So let's have a look. We've got everything. Let's put our friction back to its default, which is 3%, and everything else is in its default state. Let's hit play and see what happens. So there is our particle sim, and they are moving down. And you can see that these particles are no longer behaving like a fluid. They're behaving like as if it was sand. It's a granular simulation. And what we're able to do, if we wanted to, say, simulate this being a very dry sand, then we would reduce the viscosity setting, which would simulate a drier grain. So let's put this down to, say, 5. And now this is going to be an even drier sim of that sand. And you can see, look, it's able to kind of scatter out more as drier sand would. But for now, let's just leave our viscosity on the default 30. And now let's explore these 3 settings. So first of all, we have friction. Now this is the friction between particles. So obviously the higher the friction, the harder it is for particles to move when they are next to another particle. So if we whack our friction right up to 100%, now these particles have much more friction when they're interacting with each other. So let's have a look at the results. And here it comes. Ah, now that's interesting. So look, this has stayed together as a clump now, and it shatters when it gets to the ground. And this is looking like a really nice clumping sand. So that is an interesting effect. And that is with our friction at 100%. Now, if you require friction that is great, you need a stronger friction force, and you've got it set to 100%, and you can't push it any further, but you want more, you are able to increase the effects of this friction by adding more friction accuracy in the solve. And so, of course, to do that, we would go back to our XP FluidFX solver, and this is where we use this friction iterations parameter. This is irrelevant in fluid solves, so in liquid solves, we haven't used it yet. But if we increase the friction iterations, it's going to make that friction more accurate. It's going to iterate more times, which is going to make it stiffer. So we can increase that friction even more by increasing this friction iteration amount. It's going to simulate more slowly. You can see, look how much more slowly it's simulating. But now that friction of 100% is going to have more of an effect. You can see, look, this is a much bigger clump now, because we have effectively a greater friction, and it hasn't been able to split up as much. So let's reduce that back down to the default of 20 and return to our emitter settings. So if you're wanting nice big clumps that break apart, most of the time you're going to have your friction pretty much near 100% of its possible slider position. So now let's look at stability. Now stability looks at the particles, and it is basically a speed threshold. And what it is saying is this: if 2 particles are moving faster than this stability amount, then there will be no friction, which is what's enabling these particles to split apart. So let's do it on the default 30. And you can see that the particles that are moving faster than that 30 amount mean that the friction then gets nullified and they're able to break apart. So if we reduce the stability, this means that particles are able to break apart when they're moving at a slower speed relative to each other, which means we're going to get way more breaking apart when it first hits. And there you go, look, so it's split apart way more because that friction, that particle-to-particle friction amount is nullified because virtually all of those particles are moving faster than this stability of 5 relative to each other. If we whack it up to, say, well, let's put it on 500, This means that we're going to give it a better chance of having bigger clumps. So we've got bigger clumping. It's less able to split apart because they're not moving that fast relative to each other. And there we can see that it is created a more stable chunk that hasn't split apart more. So stability is a very useful parameter to change the way in which particles break apart, and they break apart by kind of releasing themselves of the friction amount if they are traveling faster than the stability amount relative to each other. Let's put that again back down to the default of 30. And then finally we have a cohesion setting. Now this is a kind of a springy constraint which is holding these particles together, and the cohesion amount dictates how far that particle can stretch before it is brought back. And so if we have it a relatively low amount, it means that when the particles break apart, they'll break off and they will kind of remain broken off. So let's just get this until this smashes at the bottom here. And there they are. And they kind of settle where they are. And they are their own kind of individual clumps. However, if we increase our cohesion up to 100 and hit play from this point, you'll see that they start contracting back. They're springing and being pulled back to each other to form a more cohesive mass. So the cohesion is like a springy constraint. The greater the value, the more distance the particles are able to move away from each other before they're then brought back in. And so it can give a bit of a kind of a spongy feel, a springy feel to these clumps. And look, at this amount, it's too much. It's drawing them back in and not giving us a very realistic spread. So let's reduce that cohesion amount down. So it will help hold these lumps together, but not so much that we get that kind of springy drawing in of the particles once they've spread out. So we get this nice shattering, and then they lay to a rest nicely, and the big lumps maintain their own kind of individual place in the sim. So that is the basics of how we can set up our emitters to be set to the granular mode, and we can play around with these 3 new settings to get different granular looks. And again, this shows off the power and the versatility of FluidFX, because of course we could have one emitter set to be a granular solve, so say a piece of snow, and then another emitter set to be a liquid solve, a body of water, and we can have snow or ice falling into waters. So it really is a versatile solver with lots of artistic control to be able to get the various different looks that you need for your fluid scenes.